Hi, this is the Math 125 lesson number 13 on functions and cardinality. My name is Scott Vaughn. In this video, I'll look at terminology of functions. By that I mean what is an injection, surjection, and bijection. We'll look at the cardinality of sets. We'll look at the distinction between countable and uncountable sets. And finally, we'll look at the cardinality of the natural numbers, integers, rational numbers, and the real numbers. So we'll start with some definitions. Number one, the first definition, what is a relation? So we can think of a relation as a subset of the Cartesian product of two sets. So we think of relations as correspondences or mappings between elements of two sets. So let me illustrate what I mean by that. Suppose we have a set A that is the elements 1, 2, and 3, and we have a set B that is the elements A, B, and C. So by Cartesian product, what I mean is you're creating a set of pairs where you take each ordered pair, one element from the set A and one element from the set B. So the complete Cartesian product for in this particular example would be 1A and 1 comma B and 1 comma C, and this would continue. Then we could say 2 comma A and 2 comma B and 2 comma C, and continuing we have 3 matched with every element over there in set B, so 3 comma A, 3 comma B, and finally 3 comma C. So this is the entire Cartesian product, and a relation is a subset of that Cartesian product. So an example relation could be the set R equal to the pairs, let's say 1A and 1B. Let's go, I'm just making up something at random here, 2 comma B, and let's go with 3 comma C. So what I just did there was just pick a few elements of the complete Cartesian product. Cartesian product being every element of set A matched with every element of set B, and the relation is a subset of that entire Cartesian product. And so this is an example. And so by forming this subset of the Cartesian product, I actually have a correspondence between the sets, which I can indicate, graphically with lines, specifically because these are ordered pairs. The Cartesian product is ordered pairs. You can even add a little arrow in your correspondence. So the correspondence that I've just randomly chosen comes from a subset here of elements, which is this, and let's see, we have 1 maps to A, and 1 also maps to B, and then I have 2 mapping over to B, and finally I have 3 mapping over to C. So that is the relation here, and that relation you can think of as this mapping and correspondence. So fundamentally, a relation is this sort of map between sets, uses these concepts that are sort of primitive of a correspondence and mapping between elements of two sets. So my next definition here is function, and a function is a relation between two sets A and B where each element of A is mapped to exactly one element of B, and so you can see that that functions are in fact relations, but they have an extra condition that any element in the first set A is mapped to only one element in set B. So looking back at the example that I used for the relation, that relation isn't a function, obviously, because the element 1 in set A is mapped to 2 elements in set B. So as an example, I could create the function f, which is a subset of the Cartesian product of A and B as defined previously. Let's say it's 1 maps to A, but then I can't do 1 mapping to B. I could do, let's just say, how about 2 maps to A, and 3, let's say, maps to B. So with those same sets, A and B, A consisting of the elements 1, 2, and 3, and B consisting of the elements lowercase a, lowercase b, lowercase c. What we have here is 1 maps to A, and 2 maps to A, and 3 maps to B, and then C doesn't have anything mapped to it, but the point about a function is that each and every element that's in this set A is mapped to only one element in set B. Of course, we have the function notation that we can adopt here. We could say that 1 is mapped to A by the function f, and 2 also mapped to A by this function f, and 3, it gets mapped to B. So that's the function notation that we're all familiar with, of course. And so that's the distinction between functions and relations. Functions being relations, but every element of one set is mapped to exactly one element of the other set. I guess I could also point out that we can use these terms. We call this the domain of the function, and usually call this the range, but you can also call it a codomain. And then you can actually continue to use these terms, domain and range or codomain, even when you have relations, because we have this arrow, because we have this order. We have these ordered pairs. So elements of the first set, the first coordinate in your ordered pair, that you could call the domain, even if you have a relation. You can call the second coordinate in the ordered pair the range value or codomain value. Whether or not it's a function or not, even if it's a relation, you can still use that terminology. Perhaps another thing, just because I'm also at the same time thinking about the Calc 3 class, we have functions there of several variables. So you could have elements in the domain that are not just single numbers, but are actually points, like points x and y, that map to some other set that is the real numbers, for example. So we could expand this to encompass multivariable functions. But that's the fundamental principle there as to what is a function. Let's move on to the next definition. Okay, the next definition that I'll introduce is surjection, which is a function from some set x to set y with the property that for every element lowercase y in the set y, there exists some element lowercase x in the set capital X, such that f at x produces the y value, the lowercase y value. So we can illustrate that by drawing two sets. Here's x and here's y. And what I'm talking about is that every single element that you choose over here, let's call them y1 and y2 and y3, for every single element in the set y, there is some element over here, could be x1, x2, x3, we could have different numbers of elements, but for every one of these elements, y1, y2, y3, there is some x value that produces, that is mapped to that value. So it could be that different x values are mapped to the same value, y, but for every y value there has to be something over here that maps to it. So perhaps we have a situation like that. So for every single value in the set y, there is some x value that is mapped to that. We could write this in a very succinct mathematical language as follows. We would say the function f is surjective or a surjection. In fact, let me specify specifically that the function maps from x to y, sets x to y this way. And I'll write if and only if in a very shorthand form. So the function f from x to y is a surjection if and only if, and then I'll write it like this. I'll say for every y, element of y, there exists x element of the set x, we'll say such that f at x is equal to that y value. So for every y that you would choose in the codomain, there is some element x in the domain that f at that x value produces y. So basically, another word for this is we say f is onto. So another word used to describe a surjective function is to say that it is onto. In other words, if f is surjective, let's say, in other words, if f from x to y is surjective, then f maps x onto y. So the function is onto is another kind of shorthand phrase that people would use. They could say f is a surjection, or they might say f is onto. It has the property of being onto. That is basically saying that every element of the codomain, every element of the range, is accounted for by some element in the domain. So every element that you look at in the range, there is a corresponding element of the domain that maps onto that value. Okay, so the next definition on my list is injection, and this, in the context of the terminology for functions, we could refer to this as an injective function, also a one-to-one function. And the definition here, so our definition here is a function f from x to y is injective if and only if for all elements x1 and x2 in the domain, f at x1 equal to f at x2 implies that x1 equals x2. Writing that with in a symbolic form, let's say f x to y, f from x to y is injective if and only if for all x1 and x2 in the set x, f at x1 equal to f at x2 implies x1 equal x2. Let me write the equivalent contrapositive. I can write a contrapositive of this last conditional part of the definition, that having f at x1 equal to f at x2 implies that x1 is equal to x2. A contrapositive of that last portion, that is a conditional, we can write like this. We can say f from x to y is injective if and only if for all x1, x2 that are elements of x, we could say x1 not equal to x2 implies f at x1 not equal f at x2. So for all the values x1 and x2, any two values that you could pick in the domain set x, if those values are different, that implies the outputs are different. That's the same thing as saying if the outputs equal, then the values that were inputted must be equal. A function that is injective is also called one-to-one. And to illustrate a function that is one-to-one versus a function that is not one-to-one, let's take the following examples. Let's say we have a domain x and a codomain y. Let's take elements 1, 2, 3, and a, b, c, and let's compare So I'll create two functions, one function f, the other the function g, that map values from the domain x to the range y. And because they have to be functions first, you couldn't do something like mapping one to multiple values. But of course I could map multiple values to a single range value. So we could create a mapping like this. But that is a function that is not one-to-one. And the essence of this is that there is no inverse. And so if you were to produce a function that ran the other way from the set y back to the set x, it wouldn't be a function, right? Because the a value, the range value a, isn't mapped to a single value in the new range over there at set x. So that's what this distinguishes functions that have inverses. So we would say it's not one-to-one. It is not an injective function. So to say injective is equivalent to saying one-to-one. Right? So this is not a one-to-one function, it is not an injective function. Actually, I haven't even included the value 3 as being in the domain there. It's not onto as well. It's not a surjection because not every value is accounted for, right? But perhaps we could just include something like 3 goes to the value c, and still not a surjection, still not onto, and it is not injective either because there are 2 different values of x that produce a single equivalent range value. So in other words, looking back at that definition, I'm saying that if you pick different values in the domain, you have to have different outputs, and that's not the case. I have different values. x1 could be 1, x2 could be 2, and they are different, but they produce the same output, a, and therefore don't satisfy the condition of being an injective function. I could, on the other hand, create a function so that every single value in the domain maps to exactly one value over here. But to make it injective, I can't have the 3 mapped to the b, for example, or the a. So we could do this now. This function is one-to-one. This happens to be also onto. This function is both an injection and a surjection, so you could say that it forms a one-to-one correspondence. I'll get to that in a minute. Perhaps, just to clarify a subtle distinction here, let me just add in one more range value, d, that's not being mapped to. So this is not a surjection. It's not a surjection, of course, because that value d doesn't have any values mapping onto it. So it is one-to-one, but it is not onto. It is an injection, but not a surjection. Let's move to our next definition, a bijection. So a function from x to y is a bijection, or it's a bijective function, if and only if it is both surjective and injective. You could say a bijection is a function that is both one-to-one and onto. So one-to-one meaning it is injective, onto meaning that it is surjective. And a bijection is a function that has both of those characteristics. So my next definition here is the phrase or the notion of a one-to-one correspondence. And the definition for the term one-to-one correspondence is this. I think we could just sum it up to say that a one-to-one correspondence is just a bijective mapping between 2 sets. So this is different than a one-to-one function. Right? A one-to-one function may not be also surjective and therefore not a bijection. And so there's a very subtle difference between when you say one-to-one functions and when you describe a one-to-one correspondence. To say there's a one-to-one correspondence says more than just that you have a one-to-one function. It means that you have a one-to-one and onto function, an injective and surjective function. So a one-to-one correspondence between sets implies the existence of a one-to-one and onto function between the sets. Suppose we have 2 sets, set X that contains the elements A, B, and C, and the set Y that contains the elements D, E, F. We could create a one-to-one function between them, so that A maps to D, and B maps to the element E, and let's say C maps to the element F. Let's call this big F, because I've already used little f there. So big F is a one-to-one function. So big F is a one-to-one function, but it is not onto, right? Because there's obviously this element g here that is not mapped to from any elements in the domain for the function f. You could equivalently say that f, the big F function here, is injective. It is injective, but it is not surjective. And because it is not both injective and surjective, this function illustrates that we do not have a one-to-one correspondence. That's because we cannot form a bijective function or a bijection. There's no one-to-one correspondence between x and y possible because you can't have both an injective and surjective function. Obviously, for a quick comparison, let's take the set A and the set B. Let's say we have 1, 2, 3, and let's say we have 4, 5, and 6. And if we form a bijective function, that means every element in set B is mapped to from some element in set A. That makes it surjective. And to be injective means that you don't have different values mapping to the same result over in set B. So if you take two different values, they will go to different values in set B. If you take two different values in set A, they will go to two different values in set B. So there is a one-to-one correspondence between the sets A and B because we can identify a bijective function f that maps from A to B, because there exists a bijection f between the two sets. Okay, so that was my definition F. I got a little mixed up there in my order, so now moving on to the next definition, cardinality. The cardinality of a set is the size of the set. It measures the number of elements in the set. So what will happen is we will use the idea of one-to-one correspondence to refine the notion of the cardinality of a set when we deal with infinite sets. But as I will get to that, but let me put two more definitions on here. So I'll do a countable set. The definition of a countable set is a set that is finite or has the same cardinality as the natural numbers. So we say a countable set is a set that is finite or it has the same cardinality as the natural numbers, meaning the numbers 1, 2, 3, and on forever. So that natural numbers, a set of natural numbers, is an infinite but countable set. Some people use the phrase listable rather than countable, and so that's often the term that's used. Let me just mention something like an infinite set. An infinite set A is countable if it can be put into a one-to-one correspondence with the natural numbers. Another way to say that is an infinite set A is countable if there exists a bijection between A and the set n of all natural numbers. And so finally, my last definition. The definition can be pretty simple here. We'll just say that sets that are not countable are called uncountable sets. And what that means is that it would be an infinite set, first of all, and it's not possible to create a bijection with the natural numbers. So uncountable sets are always infinite and cannot be put into a one-to-one correspondence with the natural numbers. An example would be the real numbers, as we will get to soon. All right, with those definitions out of the way, we can now get to question number 2. Explain why the set of natural numbers n, which is the set 1, 2, 3, 4, 5, on and on forever, that set has the same cardinality as the set E equal to 2, 4, 6, 8, 10, and on forever of the positive even numbers. These two sets have the same cardinality. Why is that? Let's illustrate. Here's the set of natural numbers. Let's say we have 1, 2, 3, 4, and this goes on forever. And let's create the set E here of even numbers. 2, 4, 6, 8, and that goes on forever. And we can very quickly, easily find a one-to-one and onto function that maps every element of the natural numbers to an even number. So simply put, the answer is because there exists a bijection between these two sets. We could call that bijection f, and we can actually quickly figure out what that formula would be. We could say f, let's call it n equal 2n, just because we're actually looking at natural numbers rather than just arbitrary real numbers. So if you take any natural number, 1, 2, 3, 4, and multiply it by 2, you get an even number. And that is onto every even number that is in the set E is accounted for. It will be the result of some value in the domain of natural numbers. There will be some natural number that produces that even number, and if you pick two different natural numbers, you will get two different even values as a result of this function f. So it is both injective and surjective, and therefore it's bijective. And therefore, because there is this bijection between the two sets, there is a one-to-one correspondence between them, and that means they have the same cardinality. Another way to answer that question is to say these sets have the same cardinality because there's a one-to-one correspondence between the sets, because there exists at least one because there exists a one-to-one correspondence, because there is at least one bijective function that we can think of that forms the one-to-one correspondence. There's also a really important observation here also to be made, and that is that as soon as we identify that we have a bijection, that means we have an injection, we have a one-to-one function, and so for every even number we can actually map back to a natural number. So these arrows, when you have bijections, can be double arrows. They can be pointing in both directions. They should be pointing in both directions. What we're saying now is that not only do we have a function f, we have a function f inverse that would map back for every even number. There's a corresponding natural number, and that inverse is easy enough to find for any even number. Let's say it's the even number n. What do? Just divide it by 2, and you are back to the natural number that corresponds to that value in this bijection. So yeah, for every time you have a bijection, you have a function and its inverse. Because it's injective, it has an inverse, and so you can draw arrows that point back and forth between the two sets. That's what it means to have the one-to-one correspondence, is to have a injective and surjective function between the two sets. So we're really essentially saying that the number of natural numbers, the size of the set of natural numbers, is the same size as the set of evens, which is kind of interesting because the evens are a proper subset of the natural numbers. Right? The natural numbers are the set 1, 2, 3, 4, 5, 6, 7, 8, and on forever. And the set of evens is a proper subset, only half of those numbers in a very real sense, and yet it's the same size. Technically, it has the same cardinality. The evens are 2, 4, 6, 8, and so in one sense, only half of this set, E has half the elements, but is the same size. That's kind of a striking, kind of almost paradox, but it is a result of the very careful and formal definition of the cardinality of the set as an extension of what we mean when we say the size of the set. Right? We could say this. We could measure the size of a set if it's finite, but just how many elements it has. But if it becomes an infinite set, then we can refer to a more subtle way of defining the size by talking about the cardinality, and we could say that these two sets have the same cardinality. We're effectively saying their size is the same, but we're being a little more technical in how we articulate that. So they have the same size in the sense that their cardinality is the same, which is there is a one-to-one and onto function between them, a bijection between those two functions. That is, there is a one-to-one correspondence between them. We can actually also illustrate that one-to-one correspondence right here by just saying 1 maps to 2 and back, and the 2 maps to 4 and back, and the 3 maps to the 6 and back. So every even number is accounted for by some natural number, and if you pick 2 different natural numbers, you end up with 2 different even numbers. So surjective and injective, therefore bijective, and therefore a one-to-one correspondence between them, and therefore they have the same size. Let's move on to question number 3 that I have here. Explain why the natural numbers n has the same cardinality as the integers. So if we list out the natural numbers, and here I'll say that means 1, 2, 3, 4, 5, and on. That's not 100% everybody agrees. Some people, when they say natural numbers, they include 0. Some people don't. So it just depends on what book or what class you happen to be in, how precisely you want to define. Whether you want to define it precisely as 0 included or not is choice that depends on the situation that you're in. But so if I take natural numbers to start at 1, the answer will be the same either way, of course. But so I have the natural number starting at 1, and I want to show that it has the same cardinality as the integers. So the integers, there's no ambiguity there. That is always 0 and the plus and minus whole numbers, positive and negative whole numbers, including 0. Right, so what I might do here is I'll write this out as 0, 1, -1, 2, -2, 3, -3, 4, -4, and on like that. So without explicitly writing what the formula would be, I can illustrate that there is a one-to-one correspondence between these two sets by just saying, when you list the integers, you could just count them off. This is the first one, second, third, fourth, fifth, sixth, seventh, eighth, ninth, and so on. And so that's it, simply because you can match up the first, the second, the third, and the fourth, and the fifth term in this sequence of elements in the set. That's why we say that the integers are countable and the natural numbers are countable, and we could say that they have the same cardinality. We could say these sets have the same cardinality because we can put them into a one-to-one correspondence. Or you could say because we can form a bijection between those, and it didn't actually ask specifically what that bijection is. We don't have to necessarily write the formula for it. It's just the fact that you can clearly make one that is sufficient here to illustrate this one-to-one mapping. One-to-one and onto mapping, that is a bijection or a one-to-one correspondence between the sets. So that's why they have the same cardinality. Again, it's pretty neat to think about how the integers in a naive first impression is it seems to be a bigger set, right? Because the integers include the number 1 and the number 2. It includes +3 and +4, and of course all of these are natural numbers. So it seems like the integers are much bigger because they include all the natural numbers and 0 and all the negatives. Don't you expect that the integers would have been bigger? And the answer is it isn't bigger, even though that might be your expectation. Actually, they are the same size. We call them countably infinite. Both of these sets are countably infinite because they have that cardinality of the natural numbers. That's what it means to be countable. It has the same cardinality as the natural numbers. Okay, question number 4. It says, use a table to illustrate a one-to-one correspondence between the set n of natural numbers and the set of positive rational numbers written here as Q plus. All the positive rational numbers, that is all numbers that could be written as a ratio of integers. That is another way of saying all the fractions. In this case, I'm just limiting it to the positives. We can include negatives, but it'll be easier as a first example or a next example here to deal only with the positives at first. So let's just show that the positive rationals are countable, that there's a one-to-one correspondence between them and all of the natural numbers. So it says include arrows to show the direction in which the ordering or listing of these positive rational numbers is achieved. In other words, what's number 1, 2, 3, and 4, and so on in our correspondence, or in the mapping to the natural numbers. So the table that we make looks like this. So I'm going to start off with a row 1 over 1, 1 over 2, 1 over 3, 1 over 4, 1 over 7, and that would continue on forever. And then on the next row, I'll write fractions of this form. And I'll say that continues on forever in this infinite table. Another row, 3 over 1, 3 over 2, 3 over 3, 3 over 4. Again, continues on forever. And it continues on like this, but I want to make enough here so that I can really illustrate the pattern that I'm going to follow through the table. So let's put on another row. So this would continue on forever in that direction as well. The next row would be 6 over 1, and 6 over 2, and 6 over 3, and 6 over 4, etc., on and on. And so in this table that is infinitely wide and infinitely long, we would have every single possible positive rational number. That is, every single possible positive fraction. Positive. So I'm not worried about 0 right now. We could add that in as another step later, but at the moment, again, I'm just looking at the positive fractions. And I want to show that this set of all positive fractions has the same cardinality as the natural numbers. So it's effectively the same size as just the numbers 1, 2, 3, 4, 5, and on, right? The set here of natural numbers, 1, 2, 3, 4, 5, is infinite, but in a very real sense, you might think that the set of all fractions would be even bigger because there are infinitely many fractions just between 1 and 2, and infinitely more fractions between 2 and 3. And of course, 3 is on here. It's, when we get to 6 over 2, we get 3. We get 4 over 2, it's right there. So this set of all these fractions includes 1, 2, 3, 4, and obviously many other numbers. And doesn't that obviously mean that it's a bigger set? In fact, actually, it isn't a bigger set. It's the same size. They are, both of them, countably infinite. They both have the same cardinality. There is a one-to-one correspondence between the set of positive rationals and the set of natural numbers. And it's pretty ingenious. This idea comes from a mathematician by the name of Cantor in the 1800s. Brilliant idea to show that these sets are effectively the same size. It goes like this. What we'll do is we'll start here at the number 1. So that will be where we basically map 1 from the natural numbers. We'll start there. And then we're going to weave through this table in the following way. So we'll go straight over here. This will be our second number. And then we'll go down here to this. This will be the third number in the list. So 1, 2, going from here 1, then 2, then 3. And so then what I'll do is I'll go down to this number. That'll be my fourth value. And then I'm going to go all the way up here. I'm going to skip over that, take that one as the next value. So the reason I'm skipping over that is because I don't want to include values that I've already got in my counting, because then I wouldn't have a one-to-one function. I would have two different values of the natural numbers, maybe let's say the first, and then here's 2, 3, 4, 5. That'd be the fifth value, and they're both mapping to 1, and it wouldn't be a one-to-one correspondence because it wouldn't be injective. So I have to cover every single fraction, but I can't have two values of the natural numbers going to the same result. So I got to skip over anything that I've already included. Any numbers that are the same as the values that have already been captured, we don't include them again. So that's the way you do it. Start here, go to 1/2, and then down to 2 over 1, and then go to 3 over 1, and then go up to 1 over 3, and then go across like this to the 1 over 4, pick that guy up. We haven't gotten that one yet. Then go down this way to 2/3, and then 3/2. We haven't got that, and then 4/1. And then once we got 4/1, just like I did from 2/1, I went to 3/1. Now from 4/1, I'll go to 5/1, and I'll go back up the table. However, I'm not going to pick that 4/2 because you see we've already picked it up. 2/1 is already in the list. So skip over that. Skip over 3/3 because that's equal to 1. We've already got it. So we're going to jump all those guys. Hold on. Actually, we're going to jump over the 2/4 because we already got it. It's the same as 1/2. So you're basically skipping over any values that you've already counted. So it means I'm going to go all the way up to 1/5. Pick that guy, we haven't got him yet, and then scoot over to 1/6. Once you have the 1/6, then you can travel back down. 2/5 we haven't got, 3/4 we haven't yet picked up, so pick up that guy, and 4/3 and 5/2. And then I would go to the 6/1 as the next value, and it would continue this way. So in this way, you will eventually, eventually get every single value in the table. Of course, that would take, infinitely many steps, but as you continue, you get them all. And I want to point out something that somebody might wonder, there's a possible thing that you could imagine, are there other patterns that you could follow? And one of the things that sometimes people think about is just, what if you just went down the first row, just picked up all those values? Well, doing that, if you went forever, you would never, if you continue, you'd never move to the next row. So you haven't generated an ordering or a rule to follow that would actually get everything, because you would just continue forever on the top row because it never ends, right? So you have to have something that as you actually do get everything, right? You can't just take the top row or the first column or some diagonal. You have to create a pattern that you could get any rational number as long as you wait long enough. Eventually you get there. So pick any positive rational number and eventually you reach it, guaranteed, if you follow this diagonal diagonalization or diagonal pattern, right? So that was the genius idea. That means that basically now we could say, maybe we'll put it here, we'll just say that's the first one, this is the second one, here's my third value, this is my fourth and fifth, sixth, and seventh. So here I am now counting off the natural numbers. 1, 2, 3, 4, 5, 6, 7, 8, and 9, and 10. There's 11, and 12, and 13, and 14, and it goes on. And that is the one-to-one correspondence. Now, I haven't even tried yet to actually figure out what is a formula that would actually produce this correspondence, but it's not asking for that here. It's just asking to illustrate what the one-to-one correspondence is, and so that answers that question. And actually, the next question that I have that I wanted to look at is this number 5. It says, complete the following table to illustrate the one-to-one correspondence, the bijection that's between the natural numbers and the set of positive rational numbers. In other words, list out the first 10 rational numbers given by the one-to-one correspondence that was illustrated previously. This illustrates the one-to-one correspondence. So now you can actually make it clear as to what was the first value, second value, and I'm not sure if I'll be able to see it and write at the same time. Let's see. First value is actually 1, right? And the second value is 1/2. 1, then 1/2, then 2. 1, then 1/2. This was supposed to be 2. And then the fourth value is 3, right here. The fifth value was 1/3. Sixth value, 1/4. Seventh value, 2/3. Eighth value, 3/2. You see, this is complicated, right? It's 1, and then it jumps down to 1/2, then it's up to 2, then it's up to 3, then it's down to 1/3, then it's even less to 1/4, then it's larger at 2/3, and then larger at 3. Very difficult to figure out what those would have been, and I'm not writing what the formula is. I'm just reading off my table, but it's very clear in the table how that works, right? I mean, it's just hard for me to read my own writing. But the 9th value, I can see it, it's 4. And then the 10th value, that's 5. And then this would continue, but that's all we were supposed to fill in. Just the first 10 values in the one-to-one correspondence between the naturals and the rationals. That would continue as illustrated in this table. And it illustrates the fact that they have the same cardinality. These two sets have the same size. All right, let's look at this question number 6. Prove the set of real numbers between 0 and 1 is uncountable. This is really fascinating because what we're going to encounter here is another infinity that's even larger than this infinity of the natural numbers. The set of natural numbers 1, 2, 3, 4, 5 goes on forever, infinitely large, but the set of real numbers is another level of infinity in a sense, another size of infinity, another kind of infinity that is logically bigger, and that's what we'll see here. And so to prove this is the case, we'll assume that the set of real numbers between 0 and 1 is countable, show that that leads to a contradiction, and therefore the opposite has to be true, it's uncountable. So I'll start off with, let's just say, let A equal this interval from 0 to 1. So A is the interval of all real numbers between 0 and 1. So open interval, that is, I'm not including 0 and I'm not including 1. I'm just including every value between 0 and 1. And all of these values we can write as decimal values. They may be terminating decimals, and so, but they're decimal values. They may be terminating or repeating, or they're irrational numbers and have no pattern, but they're all expressible as decimal values. So we'll make this statement. Suppose A is countable. So that means that we'll be able to form a one-to-one correspondence with the natural numbers. And all of that will lead to a contradiction, which means that we go back and say that this is actually false. Therefore, A is uncountable. That's what we'll expect to happen with this proof. That's how it's going to work. That's how we'll show that it's actually uncountable. Right? So if we first suppose that A was countable, what I'm talking about is that you could do something just like we did back there in number 5, where you could form a one-to-one correspondence between the naturals and the set A, like I did with the naturals and the set Q here. The first element, the second, the third, I can match them up. Every value in the natural numbers matched up to an element of the set here, to an element of the set Q plus, actually. This was actually Q plus, which is the positive rationals. So by assuming that A is countable, that means there is a bijection, and let's say that means there is a one-to-one correspondence between the set A and N, and so if there must be some correspondence between them, choose any correspondence that would exist. So if there is such a correspondence, let's take any possible correspondence that is a one-to-one correspondence between them, and let's just write out what it is. So of all the possible correspondences that could exist, choose any one of them and actually illustrate it. And I mean just illustrating it like we did here in number 5. Let's just list it out. I'm going to list it vertically, though. Be convenient here this time to say, let's have the natural numbers run down the screen like this. 1, 2, 3, 4, 5, and this goes on forever. And here's the set A, which is all the real numbers between 0 and 1 in that open interval. And so because they are values between 0 and 1, they can all be expressed as decimal values that start with 0 point something and then all the digits of that number. So let's describe whatever that correspondence is. It would lay out values one after another from the set A. So let's suppose the first one, whatever it was, let's just label it as having the digit A11 and then A12. And so what I'm doing here is I'm saying this indicates that it's the first value in the list, or in row 1, and this is the first digit. This is row 1, the second digit. It goes on, so this would be row 1, third digit, row 1, fourth digit. And that would all continue out to some point where you are at the nth digit, and it would continue on like that. And then the next value in my list would be again 0 point something. And so let's just label it. Whatever that value is, we'll say it's the second row, first digit, second row, second digit, second row, third digit, second row, fourth digit, and continues out to second row, nth digit. Continues on forever. Now it's possible that these values could be 0 on after a point. If you're also wondering about, like, there's a scenario here. I'm assuming that the function is 1-to-1, right? Because I'm assuming that it's a bijection, a one-to-one correspondence. Since it's 1-to-1, you can't have two different representations of the same value. So it's already sort of built into the assumption that you wouldn't have a scenario where you have repeating 9s, right? So for example, if I had 0.4 and then all 9s after that, that would be equivalent to having 0.5, all 0s, and so that doesn't happen. That's already excluded in the assumption that this is a one-to-one correspondence because it's a bijection, and because therefore it's a one-to-one function. So you don't have ambiguity in the expression of the values. 1 is mapped to this value, and this value is mapped back to 1. And likewise 2 is mapped to this value, and this value is mapped back to 2. And so each of these values in this table are distinct from each other. So the third value in the list would be, again, 0 point something, 0 point, and then it would be the third row, first digit. This would be the third row, second digit, third row, third digit, third row, fourth digit, carries on, third row, nth digit, and carries on infinitely. Maybe repeating digits, maybe no pattern at all, maybe all 0s after a point. So that just continues in the same pattern, identifying the fourth element in the list and the first digit, second digit. For example, here's the fourth element in the list, the first digit of the fourth element, and the second digit, and the third, and so on. The fifth, just like that. And that would continue on, and so eventually you're at some arbitrary value n, and that arbitrary nth value in the list would actually have the same form, 0 point, and then it would be made up digits that we will label with the value a and subscripts. And so here we'll be at the nth row, first digit, and then the nth row, second digit, nth row, third digit. A sub n4 represents the digit of the nth value in the list, the fourth digit of the nth value in the list. Right? It goes on to eventually up to the nth value in the list and the nth digit. Right? So the nth digit in the nth row, and that would continue. So looking at this n right here, this is the nth digit of the nth row. Right? So that's what that term represents. We could put that off on the side here. We could say when we talk about a sub ij, this is the j digit. We could say the jth digit of the ith value in the mapping or one-to-one correspondence with the natural numbers. Okay, so if this is a one-to-one mapping between the natural numbers and the set A, then it would continue on to be an infinitely long table that's infinitely wide to carry all of the values in the set A. So we're saying that every single value in A is included in the list, and mapped exactly to one specific value in the set of real numbers. So what I'll do now is I will demonstrate that there actually is a value that can't be on this list, even though this is an infinite list. There's a real number in the set A that isn't on the list. In other words, it's impossible to make a one-to-one mapping from the natural numbers to A that is also surjective. To do that, what I'll do is I'll focus on each of these digits right here, A11, A22, A33, and A44, A55, and all the way up to A sub nn, and I'm going to construct a value based on what happens to be in those numbers. So the way we'll construct this value, we'll call this new value D, that we're going to say exists somewhere that just can't be on this list. It has to be beyond any possibility of being on this list. And the way we construct the D value is we say D is between 0 and 1, so we'll start off with 0 point something, and we'll construct digits that we call D1, D2, digit number 3, and digit number 4, on and on and on, up to digit number n, and it would go on and on after that. And so how do we determine what these digits are? And the rule will be like this. For each value of n, when n is 1 and 2 and 3 as you go along this expression here, 1, 2, and 3, you can actually look back at A11 and then A22, A33. So the way that we'll actually determine these values, D sub 1, D sub 2, and D sub 3, and so on, is for any digit in that expansion, D sub n, what I'll do is I'll look back at the digits that are in this diagonal. And so, for example, when we get D1, what we'll do is we'll say if this A11 is not a 1, then I'll make my digit in D A1, and otherwise I'll make it a 2. In other words, I'm doing this. Make D sub n a 1 if A sub nn is not a 1, and make it a 2 if A sub nn is actually equal to 1. Right? So as long as this is not a 1, then I'll set 1 in the value for that digit in D. And if this actually was a 1, then I'll make the value 2 in my expansion for the number D. Let me illustrate sort of what that would look like. So here's an example arbitrary bijection between the natural numbers and the set A. So this would go on, and so would this. And notice it doesn't really matter. These values can be really complicated in their order, right? Because we saw that already with the rational numbers and the how that could go up and then it could go down. And so this is 0.2, and then it's 0.1, and then it's 0.3, and then it's 0.03, and up and down. Any arbitrary mapping, as long as it is a one-to-one and onto mapping from the natural numbers to the reals, suppose this was such a mapping. And so what I'm going to do is I'm now going to imagine constructing this value D from this mapping. So we're actually looking at the first digit here, and the second digit here, third and fourth, the fifth, sixth, seventh, and eighth digits, and it goes on like that. So what I want to do is I want to highlight A sub 1, 1, A sub 2, 2, A sub 3, 3. That is the third value, third digit in the third value. This is the fourth digit of the fourth value in the list. This is the fifth digit of the fifth value in that list. And so how do we construct D in this particular example? Well, it's always going to be 0 point something, and then here's the rule. If this is not a 1, then I make the value 1 here, and if it is a 1, then I put 2 in the expansion that I'm generating, right? So this A11 is not a 1, so I'll make this a 1. Now this is not a 1 here, so in the second digit, A22 is not a 1, so I make this a 1. In the third digit now, I get to the third digit, so I look at the third digit of the third row, and that's not a 1, so I'll put a 1 here. And then I look at the fourth digit of the fourth row, or the fourth value, that's not a 1, so I make this a 1. And then I'll get to the fifth digit of the fifth row, and okay, that is a 1, so now I'll make this a 2, and we just continue in that way. we could say for any value n in this list, that value of d that we've just constructed is different from each value in the list at the nth digit of the nth value in the list. For each value of n, the value of d differs from the nth value in the list in the nth decimal place. And so there can't be any bijection between the natural numbers and the set A. Perhaps you kind of might wonder, like, well, this is an infinite list. We don't see everything on the list. Maybe this value d shows up somewhere later. Just if you wait long enough, you'll eventually get to it. But that's logically impossible, right? Because the way that d is constructed, it continues an infinite expansion of decimal values. So the longer you look down this list of values in the set A, the more you know about the value d, and the more that you continue to confirm that d isn't on that list, because it's simply being revealed and constructed to be something different than every single possible value that occurs on that list of the set A. So while we had assumed that there is a one-to-one correspondence between the natural numbers and the set A, we are led to a impossible situation, a contradiction to that, where that one-to-one correspondence fails to catch every single value that's in the set A. So it isn't onto, right? So it isn't surjective. And so the fact that we assumed that there was such a thing has to be discarded. We suppose that A is countable. That leads to this contradiction that it's impossible to make a bijection, and therefore we go back to say, well, that's false. A is countable is a false statement. It's actually uncountable. Okay, so that argument that I just presented there, that the set A is actually uncountable, is also explained in our book, and that proof is also really originally from Cantor, just like the proof of the countability of the rational numbers. So both of these really famous proofs due to Georg Cantor in the 1800s. And I mean, what's so fascinating, he's really logically revealed here that there are two kinds of infinity. There's the infinity, the countably infinite of the natural numbers, and now there's another kind of infinity, the uncountably infinite of the real numbers. And so now you can see that the tools that have been invented here to make these discoveries, right, are useful in uncovering this kind of truth in the nature of numbers and infinity. And we have this sort of new language that we can articulate those realities. The fact that there are two kinds of infinity, at least. Actually, there are infinitely many. We've seen two of them so far now: the countably infinite natural numbers and the uncountably infinite number of values between 0 and 1. So this language of one-to-one correspondence and surjective and injective and bijective, these kinds of inventions lead us to these logical discoveries. This notion of cardinality is a more precise articulation of what you mean by saying the size of a set. That's useful now in this broader context. Let's carry on to number 7 here. Consider the following theorem that is proven in our book, the Discrete Math book with applications by Susanna Epp. This is in section 7.4. It says there, suppose S is any set and A is any subset of S. And then we have the statement, if S is countable, then A is countable. And the question here is to write the equivalent contrapositive. So that would be, again, with the same given. Suppose S is any set and A is any subset of S. And the contrapositive is not countable means uncountable. So if A is uncountable, then S is uncountable. And that's the contrapositive with those statements of what the sets A and S, how they relate to each other. If A is uncountable, then S is uncountable. And of course my point here is that A is a subset of the real numbers. And since A is uncountable and is a subset of the real numbers, The real numbers are also uncountable. That's actually question 8. Why can we deduce that the set of all real numbers is uncountable? Because A, the set from 0 to 1, the interval from 0 to 1, is uncountable, and A is a subset of R, the real numbers, then the real numbers is uncountable. In other words, the real numbers cannot be put into a one-to-one correspondence with the natural numbers. And so in a very real and logical sense, there are actually more real numbers than there are natural numbers. Even though both are infinite, they are a different kind of infinity in a very important and logical way. You could say the real numbers is a larger kind of infinity, another classification of infinity, a different kind of infinity that's in a very logical way bigger than the infinity of the natural numbers. So question 9 says, why can we deduce that the set of real numbers has a larger cardinality than the set of natural numbers? Well, I would answer that by saying it's because any injective function from the natural numbers to the set A of real numbers on the open interval from 0 to 1 is not surjective. And that is to say that it doesn't cover all the elements in the set A from 0 to 1. There would always be some additional element, like the value D that we constructed in that proof. This means the cardinality of the set A is actually larger than the cardinality of the natural numbers. In other words, there are more elements between 0 and 1 than there are natural numbers. And the set 0 to 1, that open interval, is only a subset of the entire set of real numbers. So, because A is only a proper subset of the real numbers, that cardinality of the set R must also be larger than the cardinality of the set N. On to number 10. Let's take a look at this one. Complete each of the following statements using the words greater than, less than, or equal. So what about part A, the cardinality of the even numbers? How does that compare to the cardinality of the natural numbers? Cardinality of the evens, that is 2, 4, 6, 8, 10, on, and the natural numbers 1, 2, 3, 4, 5. Well, we've already seen that they have the same cardinality. You can form a one-to-one correspondence between those two sets. So the answer for this is they are equal. B says the cardinality of the natural numbers is blank compared with the cardinality of the positive rationals. Actually, we did that one also already in this video. We saw a one-to-one correspondence between the natural numbers and the positive rationals. Because there's a one-to-one correspondence between the two sets, these have the same cardinality as well. So this is equal to. What about the cardinality of the natural numbers and the cardinality of the rationals? That's actually now, so this was specifically the positive rationals, and here I just have the rationals, all of them, that is including 0 and all the negatives. Well, what you could do is, if you already confirmed that the cardinality of the naturals and the positives is equal, to extend to the rationals generally, including negatives, you could just count back and forth, positive and then negative, and then back to a positive and a negative. We could actually go back to that table, right back to this table that I had listed out the correspondence between the natural numbers and the positive rationals, and just jump 1 and then minus 1, and then 1/2 and then minus 1/2, and 2 over 1 and minus 2 over 1. So we could just sort of put two layers here to this table to include the positives and the negatives. In fact, we could start at 0 and then pop back and forth between two tables, one with positive and one with negative, and so you could form a one-to-one correspondence that includes all the negatives. And so really the rationals entirely, positive and negative, also can be put into a one-to-one correspondence with the naturals, so they have the same cardinality. So that's another case where the cardinalities are equal. The natural numbers and all the rationals, including positive, negative, and 0, equal. Same cardinality. How about the cardinality of the reals and the cardinality of the natural numbers? Well, the cardinality of the reals we've now seen, already demonstrated, that that's actually greater. than the cardinality of the natural numbers. That is to say, there are more real numbers in a very logical and important, precisely defined way. There are more real numbers than there are natural numbers. So in part E, the cardinality of the real numbers on the interval 0 to 1, how does that compare to the cardinality of the natural numbers? Also, that is also greater. Even just the number of values between 0 and 1, there are more there than there are all of the natural numbers, even though there are infinitely many natural numbers. So the cardinality of the real numbers between 0 and 1 is greater than the cardinality of the naturals. Part F, the cardinality of the integers, the cardinality of the reals. Well, the cardinality of the integers exactly matches the cardinality of the naturals. We know that that's less than the cardinality of the reals. So this would be less than the cardinality of the reals. The cardinality of the reals on the interval 0 to 1 and the cardinality of the real numbers entirely, actually, those are both the same. These are equal. They are both uncountably infinite. Let's take a look at question number 11. Given each of the following functions, determine if they are surjective, injective, or bijective. Write yes or no for each of the following blanks. So here we have a function f defined from the real numbers to the real numbers. It's given by a formula, 3x plus 5, and r, of course, represents the set of real numbers. So is this injective? So what's happening here is you've got a function defined on the real numbers into the real numbers, given by this formula, which is going to produce a graph that looks something like this. And if you know some basic algebra, this is a one-to-one function, right? If you pick two different x values, you will get two different y values because you have a non-zero slope here. So because this line goes on forever in both directions, we are going to get every possible real value for some choice x. So it is surjective and it is injective. And therefore, because it's a yes for it has an inverse, right? That's another thing that you learn in basic algebra, is that if you draw horizontal lines, it's a one-to-one function. In other words, you'd be able to change the y into the domain and have another function. So that means yes, it is injective, it's one-to-one. Surjective, yes, every single possible range value in the set of real numbers is going to be hit by this function or accounted for by this function. So this is a yes. And if both of these are yes, then you've got a yes there. Bijective, it is bijective if it's both injective and surjective. Let's look at part B. So here we have a function f that goes from r plus to r plus, given by f of x equal x squared. And here, r plus, what I'm referring to, is just positive real numbers. That is, not including 0 and not including any negatives. So is this injective, surjective? Is it bijective? So let's just take a moment to think about what we're really analyzing here. There's a formula that we're all familiar with, I'm sure, the function x squared. But we're not including 0 in the domain and not in the range. So if we were to graph it, we'd leave an open circle here and then draw just half of the parabola. I think that it's also an important point that I can make right here that we are all used to looking at a formula and identifying the formula is the function. And the formula defines the rule for the function, but the function is more than just that formula. This is part of what makes the function what it is. It's part of the definition, what its domain and what its range is. So by just changing the domain, you are technically changing the function. It's not all captured by the formula. It is the formula and the corresponding domain that really define what the function is. So this is different than the function x squared defined on all real numbers. This is x squared defined on only the positives. And of course, every horizontal line is going to hit one time, so that it does have an inverse. What we're really saying is that if you pick two different x values, they will produce two different outputs. Or you could say that if you look at two, if you looked at an output where f at x1 was actually the same as f at x2, the only way that could happen is if x1 and x2 were actually the same, right? So, so That is a one-to-one function, so it is a yes on injective. Is it surjective? Actually it is, because right now the range is just all the values, all the real numbers bigger than 0, and we will get every single real number bigger than 0. As long as you get closer and closer to 0, you will get closer and closer to 0 in the output, and the bigger the x, the bigger the result. And so it is also surjective, and therefore if it's both yes here and here, then it's automatically a yes on the third one. Bijective just means that it's both injective and surjective. So we have another one that is yes on all three. Let's take a look at part C. So here I have another function that is defined by the same formula, x squared, but it is a different function because the function isn't just the formula, but also it's the domain. And I've changed the domain now to just the values are, actually all the values are, whereas before it was just positive real numbers. So now it's defined on all real numbers, and it's mapped into a different range. This r greater than or equal to 0 is referring to all real numbers including 0 and bigger, right? So all real numbers greater than or equal to 0. So that's what I'm indicating here. R greater than or equal to 0 is all real numbers from 0 on. What about with that domain and range and this rule? Is this function injective, surjective, or bijective? So once again, of course, we have the same formula. But now thinking about what's really happening, we're actually defining this on positives and negatives, and actually we will get every value, including 0, and any value going to infinity by choosing negatives or choosing positives will produce this parabola, of course. So the range is actually exactly everything is included from 0 on. So yes, this is surjective because we get every value from 0 to infinity as a result. You pick any value from 0 to infinity, and there will be an x that will produce that value. But it's not injective, right? Because this is not a one-to-one function. It doesn't have an inverse. This formula doesn't have an inverse when you choose that domain, right? Clearly, horizontal lines will hit twice, and the consequence of that is that you could say it like this. You could pick two different x values, x1 and x2, that produce the same result. Or you could say picking a value where f at x1 is equal to f at x2, it doesn't imply that the x1 and x2 are equal. So injective, that's a no. It is not one-to-one. It is surjective, but since it's not both injective and surjective, it's not bijective. So this becomes a no here. Question D. Okay, if you don't look at these carefully enough, you won't notice the difference. But of course, the formula is the same, x squared, but that doesn't mean it's the same function, right? Because it's the combination of the domain and range that actually fully define what function I have here, and of course that can affect whether it's actually a bijection or not, whether it's injective or not, whether it's surjective or not, etc. So let's say now if we include a domain that's 0 to infinity, right? R greater than or equal to 0 is this set from 0 to infinity, including 0. So if we take that as the domain, and we look again, of course, at the same simple curve, the parabola, but we include 0. So now I'm going to make it a filled-in point and a parabola that opens up, but only half, one side of that parabola. So this is a domain of real numbers, but actually just greater than or equal to 0, and this is a range that is actually R. All the real numbers, including negatives, are in this range R. So actually, of course, this formula only produces positives. So yeah, I'm starting to get at the idea, right? It's not surjective because we will never get negatives. All right, this only produces 0 or positive, and this is into a codomain or a range R, and so it's not surjective with that range. It's not a function that is onto the entire real line. What about injective? Yeah, it is, because if you pick any two different inputs x values, you will produce two different outputs. So this is a yes here, but we know now that it's not bijective because it has to be both yeses for injective and surjective to be bijective. So it's a yes, no, no for part D. I've got more. I think I got one more of these. We're almost done. How about we take a look at a slightly different formula here. This is the exponential function 2 to the power x, and it's defined on all real numbers into r plus, and r plus is this set from 0 to infinity, not including 0. So just positive reals. Okay, so what does that function look like? That can sort of help me explain and reason out what kind of, how do we classify whether it's bijection or not on these two sets. Well, the exponential function 2 to the power x, it's going to be a shape. The curve's going to look, exponential growth, looks like something like that. Doesn't really matter here, but if you put in 0, you get 1. So this is the real numbers. All these x values are the set of real numbers, and our output here is just r plus. So let's see, injective, that's a yes, because I could say the exponential function is 1-to-1. It has an inverse, which is the log function. If you pick two different x values, you will produce two different values. Or you could say if you pick one output, then the input, there's only one possible input that would give you that output. Right? So it is injective, yes. Is this surjective? Well, it is if you define it with a codomain or a range of r plus. So it is a 1-to-1 function that is onto the positive reals. So this is also a yes, right? Because every single positive real will be an image from this function. This function produces every single number, but it never hits 0. This thing will get closer and closer to 0. If you plug in -10, right, that's 2 to the power minus 10, and 2 to the power minus 10 is very small, but it's not negative and it's not 0. So it gets smaller and smaller and smaller the further you go back. The values get smaller and smaller, but always positive and never 0. And so you get every single positive real number from 0, but not including 0. From 0 up to infinity, and of course not including infinity. Infinity is not an output. It's just every value in r plus is mapped to by this exponential function. Since it's yes on both injective and surjective, then it is a bijection. So there is a one-to-one correspondence between the set of real numbers, all real numbers, including negatives and 0, and just the positives. And there we actually have an explicit formula that would actually serve as the bijection between the two sets. So that actually has the consequence to answer a consequence that answers the last question here. Finally, last one. This was kind of long, but accomplishes a whole bunch, I hope. Finally, number 12, my last question for this video. Let's look at the set R of real numbers from minus infinity to infinity, and the set R plus, which is just the positive real numbers, not including 0, all the values from 0 to infinity. So these sets have the same size, the same cardinality. Explain why or why not. So what do you think? Do the real numbers, including every negative and positive, is that set the same size as 0 to infinity? So hopefully, you would say yes because of basically that part that we just did above. But if you step back, if you just got right to this question, it's perfectly understandable somebody would think, wait, you're talking about every number from minus infinity to positive infinity, and then you're looking at just the set here from 0 to infinity. Doesn't that seem like only half as big? And in a perfectly, understandable first naive impression, you would think that they are not the same size. One, the positives is only half as big as all of the reals from minus infinity to infinity. The answer is that they are actually the same size, defined very logically as they are the same size because they have exactly the same cardinality, because actually we can see it right here in the previous question number 11, part E, right there. There's actually a bijection between the two sets, so there is a one-to-one correspondence. So there are just as many real numbers from minus infinity to infinity as there are from 0 to infinity. Amazing, right? Yes, they are the same size. They have the same cardinality because there is a bijection, or you could say there is a one-to-one correspondence between these two sets, as we have just seen in question number 11 in part E. We just saw that the exponential function forms a bijection between these two sets. So they have the same cardinality. They have the same size. Okay, that's it. That's the end of this video. Hope it's been helpful.